Okay, we're talking about session 6.1 with B period during session number 2 for spring 2021 semester. The title of the session is Estimating with Finite Sums Area Under Curve for Non-Negative Functions. Don't worry, I'll talk about what all those terms mean in just a little bit. We'll just start with a very basic question, right? Lauren's traveling at a constant rate of 65 miles per hour, so constant. Maybe she's on Highway 5 going towards Los Angeles or San Diego, where you have just flat road for hundreds of miles. Maybe you're on cruise control. I don't know. And she starts at 8 a.m. Okay, fine. What distance would she have traveled between 9 a.m. and 11 a.m.? Same day, mind you. So if you think about it, her speed is constant, 65 miles per hour, and she's traveling. And we're looking at a time frame from 9 a.m. to 11 a.m. So clearly, this is 2, and this is 65. So you can think of this geometrically, right? The area of the shaded rectangle, base times height, your base being 2, your height being 65, is 130. So she should travel 130 miles. Plus, it should be pretty intuitive, right? You're going 65 miles per hour for 2 hours, 65 times 2, distance equals rate times time, you get 130, right? Also think about the units as well, right? 2 hours times 65 miles per hour, right? The hours cancel, you get 130. Things get a little dicey with a different person. We'll look at I don't know what his names came, maybe from when Elizabeth Blanford taught this class a while back, Veronica, right? So her speed is a little different. So this is actually truly what will happen, right? Like you're on the freeway, you speed up, maybe there's slow down, maybe you see the cops, you got to slow down a little bit. So this is a little harder to do, but I know the shaded area will represent her distance traveled. So we saw that for Lauren's graph. But that's a little harder to pull off. Like, how do you actually calculate this? We do see our velocity is positive. Things get more complicated if it's not, because velocity could be negative when you turn around. Let's say you consider going south towards LA, the positive direction. So you're halfway in your trip and you realize, oh my God, I forgot like some very important item. I don't know, just trying to think out like maybe a piece of jewelry or who knows, you forgot something, right? So you turn around, so we can start to be in negative direction. Things get a little more complex when velocity changes sign. We'll explore that next week. Don't worry, we'll get there. For now, we'll keep things simple. That's what's meant by non-negative functions. So the velocity is positive the whole time. But still, this is distance traveled when you look at this, because remember, area of a rectangle is base times height. And my base is going to be time. My height is the y-coordinates, which is velocity. And so that's going to represent distance. Whenever you took your speed times time, that gives you distance, right? And it was easy to do for Lauren. A little hard to do for Veronica because her speed is not constant the whole time. So find the area in the curve turns out to be an important tool in calculus. In this section, we start by finding a rough estimate of the area by approximate by a series of rectangles. What we're going to do to estimate Veronica's area is I'm going to draw these thin rectangles and use that to approximate her distance traveled. Of course, it's not going to be a great approximation. Sometimes you could under or over approximate. But if I were to chop up her shaded region into these thin rectangles from 9 a.m. to 11 a.m., I can get a rough estimate of how far she traveled. Of course, for Lauren, it was easy because she stayed at the same speed, so it's just nice and flat. A little tougher for Veronica, right? So let's look at an example here. Example 1. Let's say your velocity is modeled using t squared plus 2. So your velocity function is parabolic or quadratic. Let's say the position is at x equals 0 when at t equals 0. So at t, your position is 0 at t equals 0, right? You want to know how far do you travel, or where's the particle at t equals 3? That's what we want to know. Okay. Well, there are several ways you could do it. Since the particle starts at x equals 0 and always travels in the positive direction, because velocity is always positive, how do we know this? Well, we know this because t squared plus 2 is never negative, right? because how can you square something and make it negative? It's impossible. You're adding 2 also. But anyway, position at t equals 3 will also be the same as distance traveled. That's not always true when sometimes the velocity is negative. Again, we'll explore that next week. But for now, the position at t equals 3 will also be the same thing as distance traveled. Also because our position was 0 at x equals 0. We're really simplifying this situation right now. We'll make it more complex next week. So whatever we're finding as our total distance traveled will be the position at t equals 3 as well. Now, how are we going to do this? How are we going to find the distance she traveled? Well, let's estimate the area between the curve and x-axis using 3 rectangles of width 1. And there's 3 different rules we can use for making our rectangles. There's something called left, right, and middle. In fact, we call it Lram, Mram, or Rram. Sounds like a computer memory chip or device or something. Let me tell you what the Rams mean. It's actually on the next page, but I'll tell you right now. The R means rectangular. The A stands for approximation. M stands for method. So LRAM is called left rectangular approximation method. MRAM is called, oh, I got mixed up, yikes. Sorry about that. RRAM is called right rectangular approximation method. MRAM is called midpoint rectangular approximation method. And I'll define it again for you guys on the next page. So how do you do this? What you do is you simply draw rectangles. And we're going from 0 to 3, mind you. So you draw rectangles like this. This is for LRAM. So what you're doing is you want the left corner, the top left corner, touching the rectangle. Sorry, touching the curve. That's called LRAM. The true area, just so you know, so here's, when you plug in 3, I think you get 11. Is that right? Yeah. The true area, just so you know, is going to be this. That's the true area. Obviously, we're not going to be able to get that. That's called LRAM. RRAM looks like this. That's when you want the right corner touching the curve. Remember, we're going from 0 to 3. Okay, that is terrible. I could do better than that. Okay. That's called RRAM. Okay, you still go from 0 to 3, but you want the right corners touching the curve. Then lastly, here you want the midpoint. So what you could do when you do the MRAM is kind of locate the midpoint of each interval. So you're going from 0 to 1, 1 to 2, and 2 to 3. So the midpoints are 0.5, 1.5, and 2.5. So your rectangles, so the midpoint of the top of each rectangle touches the curve, or the middle of the top. I didn't draw this as best as I could. It's hard. You need really steady hands when you do this. Let me maybe draw those a little better. Come on. There we go. Okay. Let me shade that also in yellow. Okay, and so what we're doing is we're deliberately going to calculate the area of each rectangles to approximate where the particle is at t equals 3, or the distance is traveled from 0 to 3 seconds. Well, this is really easy. area of a rectangle, you know, is base times height, right? So that's 1, 1, and 1. This is a height of 2, a height of 3, and a height of, I think, 5. So the area here is going to be 2 plus 3 plus 5. Oh, sorry. That's 6. Let me get my eyes checked. So the area of all these rectangles is 11. Here, the width of these are also 1 each. But the height here, I think, is 3, then 6, and then 11. So then 3 plus 6 plus 11. So the area is 20. It's pretty clear that the Lram is under approximating and the Rm is over approximating because you have a lot of overage with here. The Mram might be a little more accurate for us. In this case, your widths are still 1 each, right? You're told to make 3 rectangles with 1. We're going to actually have to plug in 0.5 into the function here. So it'll be 2.25. Plug in 1.5, that's going to be 4.25. And then plug in 2.5, that's going to be 8.25. Add it all up, and what do we get?
What are you
14.75.
plugging in?
Go ahead, question.
What are you plugging in?
You're plugging these x values here into this function. Right now, it's just kind of looking at it on the graph, the heights of each rectangle. But what you could do for an Lram is you could do f of 0, or sorry, it's v. For Lram, you're doing v of 0 times 1 plus v of 0, sorry, v of 1 times 1 plus v of 2 times 1. That was for the Lram, where I plugged in 0, 1, and 2 for x. For Rram, I'm plugging in 1, 2, and 3 for x into the velocity function. So in this case, I'm doing v of 1 times 1 plus v of 2 times 1 plus v of 3 times 1. For Mram, I'm doing v of 0.5 times 1 plus v of 1.5 times 1 plus v of 2.5 times 1. So that's when I see a question in the chat. Okay, and person correct themselves in the chat, so that's good. No question in the chat. Well, Lram, why wouldn't you go one more rectangle over? Isn't there still one more place? No, there's not, because if I redraw this, when you do Lram, you're starting at t equals 0, right? So you want the top left corner to touch it. So that's one rectangle. That's another rectangle. That's another rectangle. I've now gone from 0 to 3. If I draw another one, now I'm going from 0 to 4. So, and then for right, usually what you could do for right is you could start by going at the right endpoint at t equals 3, and have the right corner touch. So you kind of go backwards. Kind of weird. Kind of like in other languages, like I know, like in Arabic, for example, you have to write backwards or from right to left. So it's kind of going from right to left. Let me do that. Okay, cool. And of course, for midpoint, you're just going to find the midpoints for each interval. Okay, so I think it kind of explains the stuff that's on the other pages too. So we could probably go through this more quickly and do an example and get closer to a break. So again, what is this? What does the L mean? L means left. R means right. M actually means midpoint. You can say middle, I guess, but I call it midpoint. And then R is rectangular. I'll abbreviate it. A is approximation. I'll abbreviate it. M means method. So we're taking a very geometric approach for now, and we're going to connect it to calculus later in the week. And then that's going to be the basis or the foundation for the definite integral, which is the key idea for this week. So how can we make these methods more accurate? Anyone have an idea? Because obviously the Lram wasn't very accurate on the previous page, nor was the Rram. The Mram is a little more accurate, but what if I want to make all 3 of these methods accurate? I only did 3 rectangles, right? So I don't have an idea of how I can make it more accurate. You could average them. Well, if you average, you're only getting one rectangle and then times it. Well, I don't know if that really does much to it for us if we average them. But what if we had more rectangles though? What if I did skinnier rectangles? My rectangles are pretty wide right now. What if I made the width of each rectangle like 0.1 instead of 1? Okay, it's gonna be awfully hard for me to draw it, but you see I have this really skinny rectangle, and another skinny one, and another skinny one, and another skinny one, and another skinny one. So if I add more rectangles, I probably get something a little more accurate. So more rectangles is how we can make it more accurate. Which means they'll be thinner. Now, will the area Lram always be smaller than Rram? Because it was for our example we just did. The answer is no. Consider a decreasing function. What about a decreasing function? So here's A, here's B. If I do an Lram, now I'm over approximating. Or if I did an Rram for decreasing function, so you start at the right corner, you can see that you're under approximating for an Rram. So Lram is not always going to be less than Rram. Don't assume that. In fact, actually, it's sometimes asked on the AP exam, like if you did a right rectangle approximation for a decreasing function, what would happen, or which one would be greater, or whatever. Excuse me. They can't ask that. Now, Mram happen to be in between our Lram and Rram values. Will that always be the case? No. No again. And example 2 will be a good example of showing you how Mram may not necessarily be in between Lram and Rram. Notice how example 2 has a change in concavity as well. That's concave up and concave down. So when you have that kind of funky stuff happening, you can't always assume that Mram is going to be between Lram and Rram either. Now, what happens as the number of rectangles increase, we get a more accurate area. And that idea of adding more rectangles, and if you think of it as a limiting case, in fact, if you think of n approaching infinity, let n be the number of rectangles, right? So we'll assign the number of rectangles a variable, call it n. Imagine n going towards infinity. That is going to be the basis of a definite integral. We're going to talk about that later this week. We're going to use a lot of limits and calculus stuff to help us find the area between the curve and the x-axis. For now, we have approximation methods. This is how we get things started. So now let's talk about example 2. We're going to do Lram, Rram, and Mram for this function from x equals 1 to x equals 3. We're going to calculate it. And then we'll talk about kind of an AP style problem that's good example there. And then we'll talk about example 4. My guess is let's do example 2. Let's take a break after example 2. We'll come back. We'll do examples 3 and 4. Then we'll do the worksheet. Okay, for example 2, excuse me, we have x squared times sine x. Estimate area on the curve from x equals 1 to x equals 3 by using these 3 different methods. Okay. So let me partition for us here. I'm going to do 4 partitions. So usually when you do partitions, the width of each partition we call delta x. And delta x is typically b minus a over n. So delta x will be the width of each interval. N will be the number of intervals or rectangles. And of course, A and B are your endpoints. So, excuse me. So here's 1, 2, 3. And width of each rectangle is going to be 3 minus 1 over 4, because you're doing 4 intervals. You're told to do 4. 2/4 or 1/2, or 0.5. So what I'm going to do is, if I do an Lram, I'm going to make it look like this. Okay. How do I compute this? Well, you're doing 0.5, that's the width of each of these rectangles, times f of 1 plus 0.5 times f of 1.5 plus 0.5 times f of 2 plus 0.5 times f of 2.5. By the way, you can consolidate this, just push a 0.5 off to the side here, doing f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. And you punch in your calculator, because you have the function right here, right? Don't do that mentally. That's really hard to do mentally. Actually, I'd be really impressed if you could do it mentally. Plug in a calculator. So you got to plug 1 into f of x and 1.52 and 2.5. I trust you guys can do that just fine. I'll tell you how you can do it more effectively, but there's a question in the chat right now. Oh, where do you hear that we're going to red tier? Okay, cool. Okay, yeah, looks like it. Well, good. Okay, yeah, I think the numbers have come down. That's great. Okay, so if you were to plug all this in, what you could do in the calculator just to be effective with your work is this. Let me think here. You go out, no, go to y equals. Let me type as some steps. Press y equals and enter equation. Then in home screen, press alpha and then trace. Call up y1. Type in y1. Yeah, so that's how you can be effective with this. Go to y equals. So here's a calculator, right? Right. Hit y equals top left corner. Enter the equation x squared times sin x. By the way, you gotta be in radian mode. Very important. Radian mode. Okay. After you do that, and go to the home screen. When you go to the home screen, you could probably just hit second mode, quit. Just got to know, because if you hit clear, then you clear whatever you typed in. Yeah, I don't think that will do anything for us. You can graph the equation, I guess, and hit clear after that. But after you hit alpha trace, then you should see like y1, y2. So we'll call up y1, and then you'll go back to the home screen and just type in the x coordinate inside the parentheses. If you do that, then you get all these different values. So you can do f, and then you can just keep repeating it. And actually, if you hit second enter, it calls it the most previous entry, just so you know. So that's kind of the case there for that. And by the way, I'll tell you what the answer is, just to save time. The answer for this one, let me change colors here. Let's go blue or orange to say. It's going to be 5.232 if you work that out. For this one, you're going to do, same thing, 0.5 on the outside. But now what you're going to do, let me draw this for you guys. You're doing an Rram. So we start at the far right corner at t equals 3. So here's 3, 2, and 1. you're kind of going from right to left here. So that's how those would look. So you're looking at y values at 3, 2.5, 2, and 1.5. You're not going to plug in 1 because a rectangle never touches. The height of the rectangle is not dictated by F1. See here, the height of the rectangle was dictated by F1, then F1.5, then F2, then F2.5. The heights here are dictated by F1.5, F2, F2.5, and F3. So the F of 1.5 plus F of 2 plus F of 2.5 plus F of 3. So that's that. And that's actually 5.446 if we were to work that out. Okay, and then finally, any questions so far before I do part C? Okay.
How would you calculate it on Desmos?
I don't know how.
Or would you just make the, you would make the, oh yeah, I don't know how either.
Okay. Yeah, I mean, you graph it, but I think, and here's the thing too, the AP exam, for those who are going to do the AP, I'm going to push that you guys do it during administration too. I think the survey I don't think has come out yet. I really want to push you guys to do it for administration too, because I do think you guys need a little more time. I would not recommend administration 1. I'd definitely recommend administration 2, which would be May 24th. Just because we got a little bit of a later start, and you just need more time for the review. My A period says I am going to push for May 4th. My D period says I'm going to push for June 9th, because I'm not starting with them until April 26th. But anyway, the point I'm trying to make is that on the AP exam, you can't use Desmos, because it's most likely it's going to be on paper. Now, by the way, if anyone here wants to do it June 9th, I'm not going to hold that against you. That's totally fine if you want to do June 9th. I still think May 4th is really a good decision. But if you do May 4th or May 24th, it will be on paper, meaning you're going to have to use your calculator. So you have to be comfortable with that anyway. That's the point I was trying to make there. Okay, last one, Mram. So let me partition this again. So remember, we're going from 1 to 3. And now you're using the midpoints, right? So we'll see these little partitions here. But what you're doing now is you're doing these midpoints. And that's going to be one rectangle. That's another rectangle. That's another rectangle. That's yet another rectangle. And the way this works, you do 0.5, that's the width of each rectangle. But now you're doing f of 1.25. Because remember, 1.25 is halfway between 1 and 1.5. So your first interval is from 1 to 1.5. 1.25 is right in between that. That's the midpoint. Then f of 1.75. Then f of 2.25. And finally, f of 2.75. Add all that up, you get 5.661, which, by the way, is bigger than parts A and B. You can't always assume MRAM is going to be between LRAM and RRAM, let's say now. So it should be pretty simple calculations. It's very geometric, simple geometry. And again, we're just trying to find the area. Now, why do we want to find the area? Trust me, you'll see when we get later in this course, it will help us to find like the net change. Like for example, if you have a velocity curve that you're given and you find the area between the velocity curve and the x-axis, and actually find the distance you travel. Or if you have other rates, like the rate of people coming into a building, or the rate of I don't know, money coming into your bank account or something, and how much money you're going to have over a certain period of time. And maybe the money coming to your bank account is variable, right? So I mean, if it's consistent, God bless you, that's great. If people don't have that, so so anyway. So we'll take a little break right now. So here's example 3 and 4. We'll do that when we come back. Let's come back and say 2:25. So we'll take a 12-minute break. So 225 will come back. I probably need about another 10 minutes to kind of finish off these notes. They'll do a breakout session with the worksheet, which should be pretty short. We'll come back to wrap up class, but let's come back in 12 minutes, okay? And I'll actually pause the recording. Okay. So we're now talking about example 3 of the section 6.1 notes. And let me pull up give me one sec here. Hold on a sec. Sorry guys, hold on, I'm just pulling up my close this document here. Okay. Hold on, one more thing I have to take care of here. Oh, hold on. Sorry. Just kind of struggling here a little bit. Dropbox. Okay, there we go. Okay, my apologies. So let's talk about example 3. And great, I just record all my stalling there. Okay. So Mark is traveling along I-280, so Highway 280, right? At 75 miles per hour, or we'll say 110 feet per second. We see the CHP car ahead. In fact, if you guys don't know, if you head north on 280 towards Hillsborough, so if you're getting on 280 from, like, say, Woodside or Edgewood Road, before you get to Highway 92, there's usually a ramp where the cop tends to hide, just so you know. I've actually been caught there twice, but most times I usually slow down. So anyway, just good to know. But you should be a responsible citizen, doesn't want to get speeding tickets, so it slows down. And by the way, don't brake hard. Just let the foot off the accelerator. You brake hard, that's a sign of guilt, just so you know. So it shows the speed, how it's changed over 6 seconds. Find the distance he traveled during the 6-second period. Okay. We recorded his velocity values or speed values for the 6-second time frame. So what we'll do is we'll plot these points. In order to plot these points effectively, probably we'll partition the x-axis with widths of 1, like this here. I'll probably do tens. So this is speed, right? This is time. That's 20, 30, 40, 50, 60, 70, 80, 90, 100. Make sure I count that right. And then 110. Okay. Let's plot these points here. So 0, 110 is right here. 1, 99.8, kind of ballparking that. 2, 90.9, kind of ballparking that one. 3, 83.2. 4, 76.4, 70.4, and 65.1. So the curve's going to kind of look like this. It's a decreasing function, obviously. And you're asked to do an Rram for part A. So you're going to start in the far right and do a rectangle kind of like this, right? And then do another rectangle kind of like this. Another one kind of like this. And another one kind of like this. then 2 more. Just need some steady hands here, like that. I knew I was gonna mess one up. Here, there we go. Okay, just use your imagination. Okay, that's a little weird. So the way you're going to calculate this Rram area, the width of each one's 1, so I'll put the 1 off to the side here, times, I'm going to take the y values, starting with the far right rectangle. So the y value here is obviously a 65.1, right? And then I take this y value, 70.4 and 76.4. So I'm not going to use the 110 though, because none of the rectangles have a height of 110. Remember, we're doing an Rram. So I'm just going to add all these up right now. 99.8 plus 90.9 plus dot, 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 65.1. You kind of get the point, what I'm trying to add there. So if I add all those up, you should get 485.8. And this is in feet, by the way. Remember, trying to solve for the distance, you're doing velocity or speed times time. So that's the Rram area, using an Rram. Now, what if I want to do an Mram area with 3 intervals? So just to do this a little more quickly, here's 1, 2, let me change colors actually. One, 2, 3, 4, 5, 6, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. Okay. And because I'm doing, I remember we had our curve kind of looked like this a little bit. Kind of looked like that. Remember, I'm doing an Mram. Which is going to be like that. So I'm using actually t equals 1, t equals 3, and t equals 5. But the width is going to be 2. And I'm using the speed values at t equals 1, t equals 3, and of course t equals 5. Add all that up, you get 506.8. So you got obviously 2 different answers. Which one is a better answer? It's kind of hard to tell. I mean, Rram does seem to be an under approximation, so maybe the Mram is better. Now, if you did an Lram, we could do an Lram using just 2 rectangles. It's not very obvious. But here's the thing. Do I need to do a graph anymore? The answer is no. You actually don't need a graph if you know what Lram, Rram, and Mram are. If I want to do an Lram with just 2 rectangles, obviously my width, delta x, is going to be 3, right? I'll do it over here to the side. So do 3 times. If you're doing an Lram, you start with 110, because that's going to be your left corner here, right? And then you do another one at t equals 3. So you don't really need a graph if you kind of know how these techniques work. Of course, it's not very accurate, but that's what you would get if you did Lram with 2 rectangles. So the question is, you don't really need a graph. It's not necessary for these table problems. You could sort of still figure it out. But graph is nice if you have the time to do it. Lastly, area of the curve doesn't always represent distance, just so you know. It could be a lot of different things. Like in example 4 part A, what would the shade area represent? Well, here we're doing acceleration times time. That's actually going to be velocity. You guys forgot that from last semester. Because we're doing feet per second squared times seconds. Those cancel, but you have feet per second. That represents velocity. I guess you could say speed. There's a difference between speed and velocity. Speed is the absolute value of velocity. We'll explore that next week sometime. But here, you're looking at how much volume is coming into something. Maybe water coming into a tank or something like that. By the way, in Austin, Texas, they're dealing with that situation with people not having running water. They might need something like that. Water is pouring into something, right? Per unit time times time. So your gallons per minute times minutes, those minutes are going to cancel, right? You're stuck with gallons. What does that represent? That represents volume. or liquid volume, if you want to think of it that way, because it'd be weird, solid volume, how does that really work, you know, but anyway, liquid volume. So anyway, that covers the 6.1 nets. I'm gonna go ahead and stop recording.